welcome to this course on Hello. Well, hello.
5-fold cross validation. Singleton pair, triple. Solve quadratic. You kidding me? It's fun. It's very fun, you know. Wait. do you call interpretable? What do you mean? That's weird. What, pre-pruned? What is that? Is that like what the? metrics are fitted, deduplicated, and evaluated. How do they evaluate under? I mean hits, what it hits. I study papers in link production in knowledge networks. Authors usually report hits at K. I wonder how to calculate hits at K, and how does it mean about the model and the results. In a nutshell, it is a count of how many positive triples are ranked. How many positive triples are ranked in top n positions against a bunch of synthetic negatives. In the following example, pretend this test set includes two ground truth positive only. Jack born in Italy, Jack friend with Thomas. Let's assume such positive triples, identified by the asterisk below, are ranked against 4 synthetic negatives each. Now, assign a score to each of the positives and its synthetic negatives using your pre-trained embedding model. Then sort the triples in descending order. Assign a score to each positives and its synthetic negative in pre-trained embedding model. Then sort the triples in descending order. The first triple ranks second. Then sort, and then the other triple ranks first. And the other triple rank first, again their respective synthetic negatives. Then count how many positive occur in the top 1 or top 3 positions, then divide by the number of triples in a test set, which in example include 2 triples. Graph. As an API to compute hits at n. Hits at n. Hits at n. Is hit at K the same as recall at K? Recall at K? Recall. Okay. Does it help? Performance as neurosymbolic were able to perform consistently across datasets and tasks. The embedding models struggle with larger biomedical KGs. However, Trans-E performed notably well for drug-target interaction. RCGen performed relatively consistently, but achieved the middle of the pack. Any Burl was competitive and longest grab with higher ambiguity. Symbolic rules manage to cut through the noise and perform well. However, in other graphs, any rigid rules limited its expressiveness. The neural methods were better suited to smaller, cleaner biomedical kgs, and symbolic methods were to the larger, noisy biomedical kgs. They will perform consistently well across both ablations. What the hell is ablation? What is an ablation study? Cross-validated. What the? What the hell? It just means that I worked for the person who asked. Good answers are voted up and rise to the top. The best answers showed up first, so they are always easy to find. Good answers to practical, detailed questions. Okay. Cross-validated. What is ablation study? And predictors. All CNN. Right. Regional-based convolutional neural networks. Region-based computer vision, and specifically object detection and localization. The original meaning of ablation is a surgical removal of body tissue. The term ablation study has roots in the field of experimental neuropsychology of the 1960s and the 1970s. A part of the brain removed all the study the defectives had on their behavior. The context of machine learning is complex deep neural networks. Okay, let's see how Andrew Ng pronounces neural network.
I think one of the challenges of learning math and of learning certain technical fields is that there are a lot of concepts, and if you miss a concept, then you're kind of missing the prerequisite for something that comes later. So in the deep learning specialization, try to break down the concepts to maximize the odds of each component being understandable. So when you move on to the more advanced thing, we learn confidence. Hopefully you have enough intuitions from the earlier sections to then understand why we structure confidence in a certain way, and then eventually why we build RNNs and LSTMs or attention model in a certain way, building on top of the earlier concepts. I think one of the challenges of learning math and of learning certain technical fields is that there are a lot of concepts, and if you miss...
Do you know about convolutional neural networks in machine learning?
Of course, CNN is the technology behind self-driving cars and medical imaging.
What the
Hello and welcome. As you probably know, deep learning
Oh.
has already The
Hello.
term deep learning refers to training neural networks, sometimes very large neural networks, and you know the price of the outputs.
Yeah, looks like the
Hello and
a
welcome.
simple
As you probably
example of
know,
a
deep
neural
learning.
network. What the?
This is the most hardcore machine learning model I've ever built. Based on the 2016 research paper LipNet, which was
I know.
Why do you have short now? Short.
Hello, everyone. What we do now is we will autoplay. Obviously, so there's going to be 3 of the YouTube shorts. You can see how back to my homepage, and as you can see, you've let YouTube know if you have any questions.
This one.
You might notice I have no shorts anywhere in my YouTube.
Oh no, the same thing. It's the same thing. Why is this still short? Oh no. What the? Focus on questions about an actual problem. Okay, so why? Ablation study have been adopted to describe a procedure. Parts of the network are removed in order to gain a better understanding of the network behavior. Well, remove them. How about we remove them both? What the? Let's remove them already. Move this shit away. So they seem to have been together. Right? I don't know. In order to gain a better understanding of the network behavior. Causality. Complicated deep learning experimental setup. Chances are you can remove the module. What the? Causality. That's some UK.
Correlation in itself doesn't prove causality.
Causality.
Although it obviously didn't unpack causality,
ignorance over the true causality behind such issues.
Sure. Understanding the causality in your system in the most straightforward way. Is that getting complicated? Just you are moving a few modules with no loss of performance. Correct the noise. Can't fully when the moving parts. Make sure originally working was really related to the hypothesis. It's honest effort to prove your thesis. To disprove your thesis, as an example, Gashek and colleagues describe an object detection system that consists of 3 modules. Right, first propose. Within which to search for an object. Selecting search algorithm. Surely. Come on. The computer vision, right? Cascade system. Sound leaves, not color. Oh. Shit! Your wheels get part of the car because it's getting close, not because similar to the texture of the color. The final structured ways necessary to use a variety of diverse strategies. Furthermore, an image is intrinsically hierarchical, as there is no single scale for which a complete table, salad bowl, and a salad spoon can be found in A. That's so cool. Have a search by origins. Wow. Oh shit. What the? Oh shit. What the hell? Left, find any object with different scales. On the right, necessarily find an object at a different scale as the girl is contained by the TV. What the hell? The hierarchical grouping. Okay. They feeds into a large convolutional network. 5 convolutional layers and 2 fully connected layers. Help me, please. RNNMIT.
Powerful here is now we're starting to define more formally a relation between these output predictions that depends not only on the input observed, but also this past memory. And as you can kind of see and hopefully start to get intuition for.
The hell? No, this. It goes down. Went down. That's interesting. Okay, that's all the elements. Wait, so what do we do here? Just do simple math, simple data structure and algorithm class. Okay. And boom, 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 boom. And boom, 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 boom. If L1 I is smaller than L1 J, then we can go push back. Is such a thing? I forgot the append. Oh yeah, sure. L1 I plus 1. The hell is going on here? Else L n to J 1 y I m pend L1 I plus 1 y j is on n L2 J plus 1 L. Boom, 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 yeah. Detected ranges. So many zipping sequences. Oh, it's gonna zip together. Containing n tuples. Do not return as a list. Convert to a list zip object at this. Oh, it is returned and zip object at this address. At this address. Okay. At this address. Sure. Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Monday. Rainy, sunny, cloudy, sunny. Blah, 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 blah. Okay. On this day, it was weather, and the temperature was this, degree this. Okay. Ooh. Wait, what do we do with these detect ranges? List. Sort list. Transform list. 49. 37. Not pad, it's just single numbers. Result list consists. And a boom, 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 boom. It's just one pass, right? We almost run out of time, so we don't have like time for that. The hell? But wait, what the fuck am I doing? Wait, does anyone notice that I'm streaming? One view. But how do I see the comments? What the? What the hell? Oh my god. Oh my god. Oh my god. Any boob, right? Any boob. I remember someone mentioned he oh, and blah. Learning rules. That was mentioned like 29 times. Oh. Impact of multi-hop reasoning. Neuron-driven reasoning. My app was reading this. It feeds into fully connected layers. Oh my god, come. No. The hell? Oh.
This is kind of a follow-up to Bryce's videos on deep learning. So deep learning is kind of a big thing at the moment, and there's some disagreement between research over whether this is going to be big, this is it, this is the big thing that's going to change everything, or whether this is another flash in the pan like artificial neural networks were in the 80s. Everyone got very excited and they got quite good results, and then they realised that they couldn't solve all the problems with them. They don't know. For what it's worth, these are a big deal, I think.
What the?
Let's talk about convoluted neural networks. Have I said that right?
Convolutional neural networks.
Ah, right, okay.
They combine both deep neural networks, which is what Bryce was talking about, and kernel convolutions, which is what I talked about in the previous video. So I would thoroughly recommend people watch that video. You know, it's an entertaining host, right? So...
What the...
Tell me about deep learning.
Maybe it gets slightly mathy, okay? But we can just go after with an example to see what things are, right? But one typical example is if someone wants to assess automatically what is the price of a property.
But what the hell is that?
So there are certain variables that are important
It's overused.
for property, x1, x2 to whatever, a1, a2. Then the most simple way of finding an estimated value is to say, okay, I'm going to do this, a1, a2, an, plus, usually you have a bias term, something like that. This gives you the estimated price. Yeah, you can represent it like this, right? You have the input variables, and then you have your output variable, and then you do this, meaning that you have this value, you have an a1 here, and an here, and all of this is summed here into this summation.
Okay, so for instance, the larger the building, the higher the number, maybe the newer the house and the more valuable it is, or whatever.
Yeah, of which floor, whatever, right? So this is just a weighted combination of certain factors, right? So
it all comes out a big number, right?
It will, yeah. Hopefully you will have more or less accurate way, right, of describing the prices. So how do you learn this thing, right? So you can just, decide yourself. You put the 7 here, more or less what comes out makes sense, right? But usually you just find, say, 100 examples, right? If you're interested in doing this, maybe you have, a backlog of houses sold, right? And then you more or less, plot the value. In order to visualize it, we do it with only one variable, which is square meters, right? So you have one example here, another here, right? And you have this cloud of examples, right? So this means like each one of these x's is, you sold a house that has, this number of square meters for this price over here, yeah? And then you try to more or less fit that, right? So you can say, I'm gonna do like straight line, right? That will tell me, what is the relation between the square meters and the value, yeah? So now, tomorrow, someone tells you, I have like this 80 square meters house, what is the price, right? And then you come here and you say, okay, the price is this, yeah? Which is the best line? You don't know, right? That is the question. You say maybe a line is not a good thing, right? So you will use a quadratic function, right? Because, like maybe larger houses, they're more, they're not so easy to come by and usually have higher end, so things will not grow linearly.
So it's a curved line for those who are not mathematical. It's a curved line, possibly.
Yeah, it's a curved line that will involve more variables, right? And this means that you can fit things that are not so straight, right? So you have more flexibility in what you can model, right? But this comes at the cost of having more variables to describe the model, right? And there's always this type of relation, right? You have more power to represent something, and then you can capture fake correlations, right? So how to, which kind of model is best, this is something that is not clear at all, right? It's not like just throw as many variables as you can and will fit better, right? Because you will be doing something that's called overfitting, which is you will be overestimating how well you do things, right? So maybe if you put enough variables, right, and you have a set of points, right, and then you will do this, right, and you say, okay, I exactly predict everything, right? But then, the reality is that at some point you will get something there and you're totally wrong, yeah? So many parameters makes things hard to optimize, right? So in a flat structure, you have all of these, and then you have this variable that is the summation, yeah? And this is your output, right? And then you can do, as opposed to this, a deep structure, right? So
is a flat structure just kind of traditional machine learning, is it?
Yeah. Neural networks is something that has been around for a very long time. And neural network can be either shallow, right? Shallow is better name. A shallow structure, or it can be a deep structure, right?
Shallow learning, we add everything together, we come up with a number. That number gives us a how good is this or how bad is that.
Yeah.
But deep learning, other stuff's going on, right?
Yeah. So there's some variables in the middle, right, in between your input, right, the values that you're able to measure, like the size of the flat or the year of construction, and then something happens that tells you some intermediate variables right? And then from these intermediate variables, you will get the output, right? You will get the prediction. Or maybe you will put yet another intermediate set of variables and so forth, right? So the idea is you have some compound concepts, right, that might be good for predicting what you want to know. You could have a direct prediction of, you have this kind of structure that would tell you what is the price, yeah? But maybe the most relevant variables in order to decide what is the pricing is not one of these things that we're inputting. You might have to find some concepts that relate to a subset of these in a certain way, and that this is the real important thing, right? So for example, you might want to have either a very large house with several bathrooms, right? Or you might want to have a small house and then having one bathroom is not a problem, right? So this type of concept is a combination of more than one, right? You cannot decide having one bathroom is bad, right? Because it depends on the number of square meters of the house. The idea is that with deep learning, this thing here will not be the price. This will be these intermediate concepts, right? And you will say, you know, for example, I will create a concept that you have bathrooms and number of rooms on one variable. And then these other things in here will not really matter, yeah? And then you can have something here that is basically the square meters, you know, like it's an important variable independently of anything else, right? So we will keep this. This is the only thing that will matter for this variable, right? You know, maybe the year is a really good thing to have a new flat, right? But maybe if the property is more than 100 years old, suddenly, you know, it becomes really good, right? And maybe you want to have a concept that says, you know, is this a new property, or you will have yet another concept that is this a historic property, right? And this will depends on the year, but the type of relation will be different, because suddenly it's not that old is bad, all becomes good, right? So you have to have this set of intermediate concepts, right? In a way that now you can use them to decide on the pricing of your house. And these probably will be more meaningful, more representative of what people seek than just having the pure basic measurable things in isolation. So once you mix and combine some of these, will give you attributes that are better in order to predict. But you can just do it again and again, right? So there's no reason why you have to combine this thing, right, only once, right? And suddenly you want, I don't know, for whatever reason you might have a lot of market for very old houses that actually have an even number of rooms and bathrooms, right? And then you create yet another layer, right? So instead of having these connections directly to the pricing of the house, right, you have yet another connection, right? We said that we had a house with that is really old, so it just went up in value because it's a historical building. And then you have a very good configuration of rooms and bathrooms, right? So this means that, for example, this variable in here that captures whether there's a good balance rooms, bathrooms, will have a high value, right? We say that this variable is active. This will mean that you have this variable active, you have this one that was the one representing whether the building was becoming historical, right? And with these two things having a high value, then you will have a high value also for this variable over here. That will mean that you get a really high selling price in the end, right? Instead, if you have a really bad combination of room, bathrooms, right? This variable in here will have a very low value, and then instead of this variable, you will have the other one being active, and you will have a low selling value, or lower than the other case, right? So this represents the kind of choices that actually you can make when you reason about things, right? So what do you want? We want not only like square meters, rooms, bathrooms. You actually take decisions based on the combinations, right? So you will say, well, it is a large flat, but the distribution is really good, right? So this is a kind of combination of two variables, right? Having good distribution and large. Maybe if the flat was large enough, you wouldn't care so much about the distribution, right? And you can keep on having this hierarchical grouping of different variables, right? And the good thing about machine learning is that in the same way that you try to find a correlation that would explain that these things together make sense, the machine is able to find grouping of different variables in a way that you basically have no idea what it means, right? But the machine knows that this is useful to take a decision, right?
So the machine has tried out various different things, and you've told it what the endpoint is, and it's worked out what gives you the most consistent endpoint.
The machine will be able to say, okay, in order to get an accurate prediction, you have to group these variables, right, and create this kind of decision, right? So if you meet all these conditions, then this thing will have a high value, right? And whenever this thing happens, and some other decisions like that happen as well, and they have high values, right, then this thing will happen, right? And you can keep on going really deep in this sense, right? But the idea is that, right, you will take decisions based on these decisions based on the input values, right? So you will combine your inputs into some decisions that are intermediate. They are not really the pricing, right? And then you will have another layer that will decide on the price later on.
Oh, that's right.
What I would understand to be a filter is perhaps slightly different from what people who use Instagram would describe as a filter. Usually in an app or camera phone app or Facebook or some other thing where you can apply some filter, it's going to actually be a combination of lots of low-level processing of various types, you know, blurs, contrast changes, color changes. What I tend to use in my day-to-day work would be the low-level things, Gaussian blurs, edge detection, this kind of stuff. But we lots of low-level processing. Facebook or some other thing where you can apply some filter is going to actually be a combination of lots of low-level processing of various types, you know, blurs, contrast changes, color changes. What I tend to use in my day-to-day work would be the low-level things, Gaussian blurs, edge detection, this kind of stuff. But really, they're all filters, and they all take some image, process it, and come up with some output. Today we're going to look at a simple technique called kernel convolution, and that is kind of the core of Gaussian blurs and mean blurs and edge. What I would understand to be a filter is perhaps slightly different from what people who use Instagram would describe as a filter. Usually in an app or camera phone app or Facebook or some other thing where you can apply some filter, it's going to actually be a combination of lots of low-level processing of various types, you know, blurs, contrast changes.
Who is he? No. Dr. Mike Pound. Researcher. Mike Pound. University of Nottingham. Holy cow. Matched citation. Mike Pound. Q&A. Let's see his Q&A.
It just happened that we have some ties at Nottingham to Brady and Sean, who do things like number file and computer file, and so computer file was kind of fledgling. It had a bit of it was a bit established when I started doing them, and it kind of just took off really. I think because I did.
One of the interesting things, I guess, about me was that I wasn't absolutely sure I wanted to do computer science until I did it for the first time. I always had an interest in programming. I'd done a bit of programming, not a lot of programming until I did it for the first time. I always had an interest in programming. I'd done a bit of programming, not a lot of programming, but a bit of programming before I came to university. But once I started at university, I really, really enjoyed it. I loved the programming. I loved learning about cool new data structures that just, for some reason, made the same job way easier than it was before. And loads of cool stuff like computer vision and, graphics, computer graphics and writing games and things. And, I was kind of hooked after that. And then I started, programming in my own time at home for fun.
Question from me rather than the viewers then. Where would you have gone if you didn't?
Well, I considered a degree in physics. I considered a degree in biology because I find life sciences and stuff really interesting. I have absolutely no idea. I think probably biology because I think the natural world's kind of cool. But heck, I've sort of found my way into the interface. I do lots of plant imaging and stuff like that. So I've kind of got both now.
We have asked for a few questions from some of our viewers, and I'm going to pose them to you if that's all right.
Sure. Yeah. Okay.
So the first one is, how did you specialise? How did you get into doing what you do? So maybe we need a little line on what it is that you do first.
Yes, I study computer vision, so that is taking pictures and trying to colour changes. What I tend to use in my day-to-day work would be the low-level things, Gaussian blurs, edge detection, this kind of stuff. But really, they're all filters, and they all take some image, process it, and come up with some output. Today we're going to look at a simple technique called kernel convolution, and that is kind of the core of Gaussian blurs and mean blurs and edge detection and lots of other things. And it's a fairly simple technique that we use a lot around here with our computer vision work. Kernel convolution is just a process where we take a small grid of numbers and we pass them over the whole image, transforming it based on what those numbers are. And by using different numbers in the kernel, we can perform blurs or edge detection or sharpen, unsharpen, basically any effect we like. So I'll first describe kernel convolution, and then we'll look at a couple of examples of what sort of kernels that we see a lot of. Kernel convolution works by, if this is our test image, that's 5 by 5, and this is our kernel, which is 3 by 3. So generally speaking, the kernel will be smaller than the image, and usually actually quite small. And what we do, this is my movable kernel that we've come up with. Yeah? What we do, basically, is for every pixel in our image, we put our kernel over it so that the pixel is in the center. So let's look at this pixel here, number 64. We put our kernel over it, and then we are looking at the 3 by 3 grid centered around that pixel. And we take whatever values in our kernel, multiply it by 17, and then the top value and multiply it by 14, and the top corner value and multiply it by 13. So we take each corresponding image value and kernel value, we multiply them together in pairs, and then we sum the whole thing up. And then finally, we normalise by dividing by the total value of our kernel to make sure that it doesn't get brighter or darker.
So it's a bit like average.
Dividing by the total value of our kernel to make sure that it doesn't get brighter or darker.
So it's a bit like averaging, like we did in...
It is averaging, yeah. In a way, it's just a big weighted average, or if all the numbers are the same, an actual average. So, in fact, that's the first one we can look at. So if all of our values in our kernel are 1, then that's a mean blur. So if you go into Photoshop or any other image processing package and you go for blurs, blur filters, and mean, that's what it's going to be doing. This is a kernel of size 3. You usually will do it obviously centered around a single pixel, so odd sizes, so 3, 5, 7, and so on. So what we're going to do here is we're going to go 17 multiplied by 1, plus 14 multiplied by 1, and so on, and divide the whole thing by the sum of this, which is 9, and that will basically take an average. And then we'll overwrite that pixel with the output of that kernel convolution. The only thing to make clear is that we should output these to a different image, because if we overwrite them as we go, it's going to mess up the maths as we go down. I use blurs to remove noise from images before I process them in other ways for my job. Some other people might try and remove noise from images just to make them look better, or you might try and blur the background out in a photograph or something like that. And you can achieve a lot of effects just by convolving a kernel over an image. You move it around for every pixel and then you effects just by convolving a kernel over an image. You move it around for every pixel and then you look at whatever window that is the size of your kernel. The only other thing is that if you're at the edge, then you've got to make some decision as to what you do here. So you could ignore those ones and they wouldn't contribute at all, or you could wrap the image around, or you could duplicate the edge ones. You could do lots of different things. Generally speaking, I would just ignore them and then do a slightly smaller averaging for the corners. That'll mean that the blurring around the edges is ever so slightly less than the blurring elsewhere in the image, but just in the last edge pixel in a 5 to 10 megapixel image probably won't make much of a difference. So that's a very, very simple kernel. If we go for a slightly more complicated kernel, we can go for the normal distribution for Gaussian blur. So Gaussian blur is extremely common, probably, I suppose, the most common blur. It's a little bit more controlled and edge preserving than a mean blur, and so a lot of people like it. So a normal distribution is a bell curve. So if we have our axes there, and we draw a bell curve, and the standard deviation of this curve, so the standard deviation is essentially the average distance from the mean of all the points, will determine how wide this bell curve is. So a really large standard deviation will have a really large bell curve, okay? So a really large standard deviation will have a really large...
What's that? extend the list by appending all the items from the iterable, similar to an list. Zip them together. The hell it is. So this zips. So we're just gonna press and 4 and zips. Then we're gonna press extend that, press go here. I thought it was always an iterable. That is not correct though. What is going on? Zip the lists.
Bell curve, okay? And a really small standard deviation will have a really tight bell curve, which is essentially really prioritising the weights in the middle. Now, if we weight these numbers based on the values from our normal distribution, then we get a Gaussian blur. An example of a very small Gaussian kernel would be a 3 by 3. So these values are going to be, floating point decimal values, but we just simplify it a little bit. So 4, 2 on the edges, and 1. Now, the crucial difference between this and the mean blur is that we're really prioritizing those in the middle. The further away you get from the pixel of interest, the less weight you have in the combined average. And that's important because it basically means that you're not going to be blurring too much. Where there's an edge, let's say a sharp change in intensity, as you approach that edge, you're not going to be taking too many of those pixels. And this Gaussian blur can obviously get a lot bigger. So in your image processing program, you might have an option that says standard deviation or radius. And what that's really referring to is the standard deviation of the normal distribution that produced this kernel, and also the width of the kernel. So we have to increase the size of our kernel as the radius of the Gaussian function increases. This is a very small normal distribution. If this was a bell curve, it's really steep. If we had a bigger standard deviation, then we're going to need a bigger window to be able to hold enough information. This isn't near big enough. So let me draw a test image, and then we'll do a blur on it and see how it works. So this is a good sized image. This image is pretty basic. It's an edge. So we've got an area of 50 intensity and an area of 100 intensity. Just put our mean one here as well, just for comparison. So if we do our mean first, so we put that on, let's say, this 50 here, which is right on the edge. Okay, so we put our kernel on there, and we're going to be doing 50 times 1, plus 50 times 1, plus 100 times 1, and so on. So it's going to be 100, 200, 300, 400, 500, 600. And then we divide that by 9, and that gives us 66.6. Okay, and we'll round it to the nearest integer value. For a Gaussian blur, with this Gaussian blur here, we're going to be doing 50 times 1, plus 50 times 2, plus 100 times 1, and so on, okay? And that will be a value of, this is where we cut, so it's 1,000, these add up to 1,000, divided by 16, which is 62.5. So, ever so slightly closer to these 50 values on this edge than perhaps the mean blur was. It's subtle, but the edge has been slightly preserved, and generally speaking, we're giving more weight to the numbers really, really close. The edge is 50, which is 62.5. So ever so slightly closer to these 50 values on this edge than perhaps the mean blur was. It's subtle, but the edge has been slightly preserved, and generally speaking, we're giving more weight to the numbers really, really close to us. These are very low-level filters. These are the sort of filters I will use in my day-to-day work to alter images that I need to analyze. But on Facebook and on all these camera apps for your phone, you'll see a lot of other, perhaps more complicated filters, bloom, sepia, vintage ones that make it look like some camera from the 1800s or something like that. And really what they're doing is nothing hugely complicated. They're just chaining together low-level image processing. So a grayscale filter, maybe a bit of blur, and then some kind of border to make it look good, and things like this. So really, these kind of filters are at the core of a lot of the stuff that you see, even if you might not know it.
But that's it.
but because if you don't know what a kernel convolution is, this isn't going to make much sense to you. Okay, so watch that video first.
So that's the kernel convolutions we did on graphics and things like Sobel operators.
Yeah, Sobel operators, Gaussian blurs and things like this. Okay, Sobel operator in particular, and edge detection. So if we think back to a traditional artificial neural network, okay, what we've got is we've got some kind of input we're trying to learn. Okay, we've got some hidden layers, right, and then we've got some output layers. Maybe there's just one, I don't know. Okay, and these are fully connected, so we have lots of connections from here and here and here, and then these are connected to here, and so on. I'm just drawing in a few of them, and then these are all connected to the end. Okay. Now, using Bryce's analogy, we were talking about house prices. Okay, so this would be something like number of bedrooms. Okay. Now, using Bryce's analogy, we were talking about house prices. Okay, so this would be something like number of bedrooms, and this would be something like has it got a pool, and this would be what floor space is it, and has it got a good garden, and so on. Lots of these. Okay, lots of in and no's that we don't really care about particularly. Oh, I don't.
Let's see if anyone comments on our videos, our live stream. How do I see it without having to, really get into the nothing.
Good garden and so on. Right, and so on and so forth. And then finally at the end we have a house price. Now what this house price is a complicated function of these inputs. It's complicated because this node here is some linear or non-linear now combination of these. Okay, so a bit of this, plus a bit of this, plus a bit of this, plus a bit of this, through some non-linearity function. This is a different combination of these. This, again, different combination of these, and so on, right? And then this, a different combination of these. So you can see you're building up some kind of level of abstraction here, where you've got combinations of combinations. Okay? And that function is very complicated. When Bryce talked about a black box, in some ways that's exactly what it is, because we can't look at these individual weights and say, well, that's got 0.2 of this one, so that must mean this, because we just don't know what it means, right? In the grand scheme of the black box, in some ways that's exactly what it is, because we can't look at these individual weights and say, well, that's got 0.2 of this one, so that must mean this, because we just don't know what it means, right? In the grand scheme of things, in this whole network, we don't know what that individual weight means, okay? And to be honest, we might not even care that much. What we really care about is how well does it predict house price? How accurate is that based on that for a different input? So we change this, read the output, is it good? Yes, brilliant, okay? Now, for images, which is obviously what I spend most of my time around, this is a start, but it's not very useful to me. If you think that this is our inputs, okay, and I give you a picture of a house, and I say, right, tell me how much this house is worth, okay, well, what? So how do okay, so there's two things I could do, right? First of all, I could try and calculate things like number of bedrooms and stuff based on the image and put them in here. In some way, I'd be calculating some features, and then I'd be putting them in here and learning on those features. That is quite a smart way of doing it, because apart from that's obviously quite difficult. It's smart because we don't have to have that many more neurons. In anything, we can actually use the same network as we used before for our model on our house. All we have to do is work out the bit of code that does the image analysis. Now, anyone that's tried to find out the number of rooms in a house based only on one picture of the outside of the house will tell me that that can't be done, right? That's hard. Okay? So you could naively think what we could do instead is just put the image in here. Make this the first pixel, and this the second pixel, and this is the third pixel, and so on. Okay? The image based only on one picture of code that does the image analysis. Now, anyone that's tried to find out the number of rooms in a house based only on one picture of the outside of the house will tell me that that can't be done, right? That's hard. Okay? So you could naively think what we could do instead is just put the image in here. Make this the first pixel, and this the second pixel, and this is the third pixel, and so on. Okay? Then this has got all the information it could ever need, right? But that's the problem. Okay? 7 megapixel image. That's 7 million input nodes. Let's say we have 7 million loads on the next layer. Each one connects to each other one. You can see that that's just going to melt my computer. It's not even going to try and create it. It's too much information. Okay? That's why we downsample our space a little bit. What we would usually do is calculate some small subset of features, and then we will put them in at this end. So that's quite important. So traditional machine learning is done a bit like that. So Michelle's done some videos on this. Calculate some features about someone's face and put that into some machine learning algorithm. What you don't do is try and put the machine learning algorithm just on the face, because there's too much information there. Until now, okay? Right? That's where convolution some machine learning. Michelle's done some videos on this. Calculate some features about someone's face and put that into some machine learning algorithm. What you don't do is try and put the machine learning algorithm just on the face, because there's too much information there. Until now, okay? Right? That's where convolutional neural networks step in. So convolutional neural networks replace each of these nodes with a kernel convolution, so like a Sobel edge detector. Okay? Now, so instead of what I would have done before, which was run a Sobel over something and then machine learn on that, I just give this the opportunity to learn which features are interesting. Maybe it is an edge detection, maybe it's a corner detection, maybe it's something that highlights whatever's in the middle of the picture. Okay, or something that highlights the top left-hand corner. It doesn't really matter. And the point is, I don't know what they are. Right? If I give you, 2,000 pictures of houses and ask you to predict house price based on the pictures, right? I don't know for sure. I can guess that it might be how many windows it has and things like this, but I don't know for sure. Okay? And a computer can brute force through those things much quicker than I can and tell me. Okay? And then I can both predict it and I can look back and say, oh, it was windows after all. So let's imagine that what we have is our image. Okay, so I'm going to move away from the house analogy now because I'm going to have to draw a lot of pictures of houses if I do that. Okay, so let's talk about how CNN works and why it's useful. So we have an image of something. Now, I have seen convolutional neural networks used for non-images, but for now we'll just talk about images. This is a picture of, let's say, me. It's, it's not a great likeness, but I'll stick by it. Now, there are 3 channels here. Okay, so this is actually a 3D volume in some sense. Remember when we talked about 3D images? You could view RGB as, in some sense, 3D. So the first plane is R, G, and B, or vice versa. What we do is, if we perform, so remember when we talked about, there's the images, you could view RGB as in some sense 3D. So the first plane is R, G, and B, or vice versa. What we do is, if we performed a Sobel edge detection on this, what it would do is produce another image that was slightly smaller than this and only 1 deep. So hypothetically, it would be another image where the edges, slightly smaller than this, and a edge detection on this. What it would do is produce another image that was slightly smaller than this and only 1 deep. So hypothetically, it would be another image where the edges, let's say the horizontal edges, were highlighted. So it would kind of look like that or something, I don't know, some half of my face where the horizontal edges are highlighted, okay? It's not a great diagram. But there would only be one output because Sobel just outputs a number highlighted. So it would kind of look like it would be another image that was slightly smaller than this and only 1 deep. So hypothetically, it would be another image where the edges, let's say the horizontal edges, were highlighted. So it would kind of look like that or something, I don't know, some half of my face where the horizontal edges are highlighted, okay? It's not a great diagram. But there would only be one output because Sobel just outputs a number between 0 and 255, as long as you scale it, okay? Now the problem is that I don't know that Sobel's the best thing for this task. Okay? It might be, right? It might be useful to detect edges on houses to work out what their prices are, or if you want to detect faces, to detect the sides of the faces. That kind of makes sense. On the other hand, it's going to produce a lot of erroneous bits. If I'm sticking in front of a tree, there's going to be loads of edge stuff going on there that I don't care about. In a convolutional neural network, what we do is we do, let's say, 60 of these on the first layer. So we have one, and then behind it we have another one, behind it we have another one, behind it we have another one, and so on, going this way. So the first one will be some convolution process applied to this whole image that takes 3 input channels and outputs 1 output channel. The next one will be a different kernel convolution operation. So each of these will have a different kernel. Those are our weights. Those are these values here, sort of our analogy back to normal learning. And so let's say we have 60 of those or 64 of those. Okay. One of them might be detecting edges. One of them might be detecting corners. And then we use them as our features for learning. Now that's a start, but this is deep learning now, right? So what do we do now? Well, what we now do is we do more features based on these features. So we find combinations of corners, combinations of edges that make something interesting. My face is not just a circle of edges. What it is a number of corners and edges and bits of texture and things, all in a specific shape that is unique to, well, certainly to a human face, but even unique to me, right? These are capable of distinguishing between different people. So this kernel window will go down to this pixel here, okay? So this will slide about this image and produce this output image. And then the next one will do the same, and the next one will do the same. Then we do the same thing on this one. Let me do it in a different pen so we can see better. Here's my red kernel convolution, and this slides about and produces another image which is a slight combination of maybe corners and edges or something. I mean, if it's second level, it's not going to be too abstract, but we'll get the idea. Okay, so there's going to be some sort of shape that it's going to be it's not going to make much sense to us, but it'll make some sense to this machine. And there'll be another set of these, so there'll be lots of these, right, going back. All of these will look different and be some different representation of my face transformed in some way to be useful. Okay? And again, I haven't picked these. These have been learned just like a normal deep learning algorithm. So I haven't had to say, I definitely think edges are important for this, because I don't know for sure. So this goes on, and we keep doing this. And sometimes we also downsample the size of these images just to save memory. Okay, but we won't dwell on that too much. And because of the way that we downsample, and the way that sometimes these convolution operations slightly shrink the image, because they don't go all the way to the edge, right? If you've got a 5x5 kernel, you can't go to the edge 2 pixels because you're going off the edge. So we don't worry about that. We just get slightly smaller. In the end, we end up with a much smaller image and lots of features going all the way back. So these are my different convolutions of convolutions of convolutions of convolutions. And each one will look different and represent something different, and we don't know what that is. So this one could be highlighted when there's a face in the middle, or it could be dark when there isn't. This one might be highlighted when there's an ear at a certain position, and so on. Eventually, these will get down to being just 1 pixel and very, very long. So essentially what we've done there is we've completely removed the spatial dimension. There's no more spatial information left. We don't know where anything is, but we know what it is because it's listed in all these features. These now are our thing is, but we know what it is because it's listed in all these features. These now are our neurons at the end. So we have a couple more layers that point to these, and then finally we have one at the end that says, is this a picture of Mike's face? Okay, and it produces a 1 if it is, and a 0 if it isn't. And then what we do is just like a normal network, we train it. So we say, here's a picture of like me, okay? So this should be a 1, and let's say it's a 0.5, okay, because it's kind of random. So we adjust these weights, and we adjust the weights inside all these kernel convolutions.
So does that adjustment happen manually?
No, it happens using a, well, it's coded in, but it's usually performed by a library, convolutions.
So does that adjustment happen manually?
And we adjust the weights inside all these to 0.5, okay, because it's kind of random. So we adjust these weights, and we adjust the weights inside all these kernel convolutions.
So does that adjust?
So we, okay, so this should be a 1, and let's say it's a 0.5, okay, because it's kind of random. So we adjust these weights, and we adjust the weights inside all these kernel convolutions.
So does that adjustment happen manually?
No, it happens using a, well, it's coded in, but it's usually performed by a library, and it's using a process called backpropagation. So what we do is we basically predict what direction we have to move the weights in to improve our output, and then we move them ever so slightly in that direction. And we have to do it in reverse order. Because these ones depend on these ones, depend on these ones, and vice versa, what we do is we say, well, look, given that I've said it's 0.5% chance of Mike, and we want a 1, how do I change these weights here to get slightly closer to 1? And I do it. And then I say, how do I change these again to do even better? And so on, and I work my way back, okay? That kind of maths we're not going to go into. Right? A lot of these things are implemented in libraries. So as a researcher, I mean, much as I'd like to implement some of these things, it takes quite a long time, just because programming takes a while, right? And it's better for me just to apply these things and get good results than it is for me to reinvent the wheel all the time, constantly. If everyone was programming the same things over and over again, no one would get anything done, right? Because I'd have to start by programming up Linux to get, I'm not claiming I can, by the way, and so on. So, you know, let's not reinvent the wheel. So I do this, I send them, let's say, 1,000 pictures, 500 of which are me, you know, so I've been to a photo shoot or something, right? And 500 of which are not. And I train it so the convolutions and these weights on the output are such that it gets 1 when there's a picture of me and 0 when it isn't. Okay? And then I can look at these convolutions and say, what is it about me that's distinctive? And it's probably going to be finding, you know, weird shapes on my face, right? Because it's a bit of a weird shape. So things that are unique to me. Now, in a more general situation, there's a big database called ImageNet, right? They have a competition every year to see who can classify these images the best. So dogs, cats, planes, trees, and so on. Okay, they're all in there, and there's 1,000 or so images of each, right? So we have a really big network that's much bigger than this little one I drew, and we say, right, let's throw millions of images at this, right? Thousands of cats, thousands of dogs, and we have lots more outputs than just the one. And we say, what is it? And it's a dog. And it is. Convolutional neural networks have been around for a little while, but they really started to be big in about 2012 when someone came along, applied one of these to ImageNet and got incredible results, and so on and so forth. And now there's this big push and everyone's trying to get even better results and even better results. Now, I work on more of the applied, and someone came along, applied one of these to ImageNet and got incredible results, and so on and so forth. And now there's this big push, and everyone's trying to get even better results and even better results. Now, I work on more of the applied end of computer science, so I'm more interested in how this affects plant science and things like this. So that's what we're working on. But the kind of results we're seeing are really, really impressive. So, I mean, case in point, I've done some root tip detection, so detection of root tips in images, right, of plants, and I've got some software that I've already programmed, and I've kind of done a low-level feature detector approach to detecting root tips, and it's about 70%, okay, which is what you would expect, because maybe some root hair gets confused with a root tip, or a bit of blotch of dirt, or maybe there's just two root tips really close together and it gets confused. Okay? The CNN that I trained is 98% accurate, and it finds them with 99% accuracy. It doesn't make many mistakes, right? And that's over thousands of images.
So does that mean the work you've done already just goes out the window?
Yeah. No, to an extent, yes. So to an extent, no. You need expertise to be able to craft a network and train it and prepare the images. And there's obviously work to be done. And there's some disagreement over how much of a problem you can solve with a convolutional neural network, right? So there are lots more things you can do with roots beyond finding tips. Can you do all of them with a convolutional neural network? I don't know, we'll see. I'll be trying, but we'll see, okay? Maybe not. So maybe what you do is you use this as a tool, just like other machine learning algorithms, within a package that does lots of other things as well. On the other hand, if you're just doing cat and dog detection, you might as well use a CNN, because it's going to do better than everything else. If you're just doing cat and dog detection, you might as well use a CNN, because it's going to do better than everything else.
That's interesting. Support most vector machines. In order to get a better understand of the system, or the performed an application study. Which allowed the authors to conclude much of CNN representational power comes from its convolutional layers rather than for the much larger densely connected layers. Metrics are likely to differ depending on the application and type of model. In the context of the example is of a linear regression. Well, that was kind of horrible. I low-key wanna see what's he up to. Probably no one has commented it. Go for a walk and arrive at the answer. Reasoning over paths in knowledge bases using reinforcement learning. Reinforcement. Isolate the impact of single half vector space. Intro. Sure.